Hi, we'll talk about chi-square test and distribution. The table of contents is as follows. First, definition of chi-square distribution and MGF. Second, stimulation of chi-square distribution. Third, utilization of chi-square distribution. Fourth, chi-square test and Pearson chi-square statistics. Fifth, goodness of fit test. Sixth, cross-tabulation analysis.
Let's first look at the chi-square distribution and see how it is defined for a chi-square statistic. If we define k independent and standard normal random variables for positive integers k, the chi-square distribution of degree k is the distribution of the next random variable, q equals sigma I1 to k chi I squared. Of course, you may not know from the definition alone, so we'll explain the distribution first and explain it in more details later. And before entering the chi-square distribution simulation, we will first explain the function used to obtain the mean and variance from the chi-square distribution. It is called moment generating function, and the moment generating function of the chi-square distribution with degree of freedom v is the following equation. mt equals 1 minus 2t to the minus v second. Through this, the average and variance of a chi-square distribution can be calculated as follows. m prime t equals minus v second times minus 2 times 1 minus t 2t to the minus v second minus 1. And u equals m prime 0 equals v. m2 prime t equals minus v second times minus 2 squared times minus v second minus 1 times 1 minus 2t to the minus v second minus 2. And eu squared equals m2 prime 0 equals v squared plus 2v. And then variance u equals eu squared minus squared of eu equals 2v.
Then let's see the various degrees of the chi-square distribution. If the degree of freedom is 1, 2, 3, and 4, the shape comes out like this, but it goes to the left and moves to the right. In this graph, the degree of freedom is 1 in this blue graph, and red one is 2, yellow one is 3, and purple one is 4. The term degree of freedom stands the number of the sum of standard normal distributions, as we can find out from the formula itself. Then let's talk in more detail about its reason by a simulation. When the freedom of degree is 1, first, a sample is extracted from the standard normal distribution. Then draw the sum of the values of the extracted samples as a histogram. Let's say we repeat this process for 1,000 times. The results are as follows. It can be seen that the largest number from 0 is counted, and the frequency decreases as the number increases. The reason is that in the standard normal distribution, the probability value is the largest in the center of 0, and the probability value decreases toward both ends. Similarly, even if the degree of freedom is 3, the simulation is conducted by repeating the process of extracting 3 samples from the normal distribution and representing the sum of squares in this histogram. The resulting form has the largest value at 1, and the probability value decreases from a number after 1, similar to the form seen in the previous freedom graph. So why do we have to square and add up random variables from the standard normal distribution? This is because chi-square distributions can be helpful in analyzing errors or deviations. They usually model errors as normal distributions. Let's say, for example, we create this session model. Here, the actual values are black dots, and the model values are linear regression distribution in the center. When a linear regression model is created through errors in model values, which are black dots, it is assumed that the error comes from a normal distribution. If so, the errors can be modeled here through the sum of the squared values. We can also see if this error is beneficial. In addition, according to the central limit theorem, if the number of samples is numerous and the error is defined using sum, the distribution of the error is normal. For example, mean square error is the total number of output values divided by the predicted value minus the target value added to the squared value, indicating that it is related to the chi-square distribution because it also follows the normal distribution. In conclusion, using the chi-square distribution is to verify the error. The utilization of the chi-square distribution is important in that we can determine whether this error is accidental or has hidden meanings, because the error is usually due to unpredictable reasons.
We've just talked about statistics and distributions, and to talk about chi-square test, there are two main tests using chi-square. It is goodness of fit test and cross-tabulation analysis. Usually, what we see in textbooks is about cross-analysis, but in fact, the chi-square test should be mentioned first for the goodness of fit test. In both cases, the following equation is used to obtain the chi-square statistic. X squared equals sigma squared of the observed frequency minus expected frequency divided by the expected frequency. And this equation is also called the Pearson chi-square statistic. This equation appears to be the different value for the chi-square statistic initially presented. The chi-squared statistic seen earlier refers to the sum of squares of variables that follow the standard normal distribution, but here, as I just said, it is the square of the observed value minus the expected value divided by the expected value. In other words, it can be seen that it is normalized using the expected value by summing the squared errors. You might wonder, shouldn't it be divided by the standard deviation, not the expected value? And yes, it is right to divide by the standard deviation. However, it cannot be divided by the standard deviation. So the degree of freedom is reduced by 1. In the end, it follows a chi-square distribution with one lower degree of freedom. In other words, when following the k categories, the degree of freedom of k minus 1 is followed.
Next is goodness of fit test. Goodness of fit test is comparing the distribution of theoretically expected frequencies with the distribution of observed frequencies with one independent variable. For example, suppose you randomly fit 100 products from a factory mixed with 5 types. We predict that there will be 20 products each, because we think there are 5 kinds of types evenly mixed. When we observe the frequency of products that has been chosen, can we say that the 5 kinds of types in the factory are evenly mixed? The answer to the question is what you want to see in the goodness of fit test. When the result comes out like this table, it can be assumed that this factory had been most furniture because the actual number of even ones has the most furniture. Using the chi-square statistics, you can get a value of 7.9. The top 95% chi-square value is 9.48 since it was just a category 5 and the degree of freedom corresponded to 4. In the end, our statistics are lower than X value corresponding to the top 95%, so it is difficult to say that there was significant differences. In other words, it is hard to tell that the 5 types of products in this factory are mixed in different proportions. Maybe I couldn't pick up the products evenly by accident. Next is cross-tabulation analysis. Cross-tabulation analysis is analysis method applied when there are multiple categorical variables. In other words, find out whether the difference between categories of several categorical variables significantly deviates from the expected value. For example, when we investigate what age people who feel depressed belong to, we want to find out at what age the ratio of men and women differs significantly. We can see with our eyes that women make up a much larger proportion in their 30s. Is this statistically significant? The method of calculating expected values from observations is as follows. The expected frequency can be divided by multiplying the total number of rows by the total number of columns. For example, expected frequency of men and teen cells is 17.4. Calculating all expected frequencies is calculated as follows. You can calculate all expected frequencies and calculate statistics. Let's calculate the Pearson chi-square statistics. If the number of rows in the table is R and the number of columns is C, and degree of freedom is R minus 1 multiple C minus 1, and the result has come 3.7. And the degrees of freedom are 2. The top 95% of chi-square degrees of freedoms are 5.99. So the statistic 3.73 we obtained is less than 5.99. Therefore, it can be seen that it does not deviate significantly from the expected values for gender and age. Thank you for listening.